Yeah, welcome to today's session. So, today's session is a continuation of the last session where we discussed quadratic forms and we solved some problems, and also we discussed rank, index, signature, as well as properties of quadratic forms, right? So now today we'll continue the discussion where we'll try to prove some of the properties related to quadratic forms. Okay. So just a minute. This seems some. Just let me check before starting. So just 1 minute. So we'll start the session. So we'll discuss properties related to quadratic forms. So this is as discussed. This is a continuation of the previous session where we had the introduction as well as the particularly the nature of quadratic form, which is very important. That is what we discussed in the last session. Right. So here, so first what we do is quickly we recall the few things related to quadratic forms. That is, so the definition of quadratic form and matrix representation of quadratic form, uh, and also the definition of congruence of matrices, and also the congruence of quadratic forms. Just a recap of the discussion what we had so that we can continue the same in the today's session. So first thing is what is the definition of a quadratic form, right? So quadratic form is nothing but a polynomial of degree 2, right? And also this it should be a homogeneous polynomial, right? So homogeneous polynomial of degree 2, and it can be in terms of any number of variables. There is no restriction on the number of variables that it should contain, right? Clear? So here this is one example. So 2x square plus 8xy plus 7y square. So it is a polynomial, right? And it is a homogeneous polynomial. So you see here, this is x square, and here it is xy, and it is y square, right? So it is a homogeneous polynomial of degree 2 in terms of two variables here, in terms of x and y. So that's why this is called as a quadratic form. Okay. So next, so how to represent the quadratic form in terms of matrices, right? So as discussed, so now we can write this as the, here it contains two variables x and y, right? So this is a column vector with which consisting of all the variables here, all the variables in sense x and y. And here it's a transpose. There is a column vector, here it is a row vector. That's why this we write as x transpose. Generally here we are denoting it by A. And this is a matrix, coefficient matrix, right? So how to have this matrix? Just a recap of what we discussed is, so here this is x square term and this is this y square term, right? So here 2x square, so 7y square, and next 8xy is there, right? So this term is xy term and this is yx term, right? So here we have to distribute equally, right? So 4xy as well as 4xy. So every quadratic form can be written in matrix form as x transpose Ax. And one thing we can observe, this A is always a symmetric matrix. Symmetric matrix means whenever a matrix satisfies the condition that is A transpose equal to A, right? Then we call it as symmetric matrix. So this is. So one more example. So to say that it can contain any number of variables, right? So here 2x square, 2yz, 4xz, 3xy, 6y square, 7z square, etc. From this we can observe it contains three variables x, y, z. So we'll take x as a column vector consisting of x, y, z, and it's a transpose, that is a row vector, x transpose, right? So now what about matrix corresponding, right? So how we do is, generally for our understanding we can take x, y, z as shown here, and this diagonal elements are coefficients. Now if you see here, this is x square, this is y square, and this is z square, right? So one by one we can take. So 2x square, so 2x square, right? So next 2yz, right? So this we have to distribute equally, where yz half with zy. So yz is where, so this is yz, right? So half here, that is 1. Zy, this is, right? So this is over. Next 4xz, right? So we have to distribute this into 2xz and 2zx. So this is xz, right? So 2 here, and this is zx, 2 here, right? Next 3xy. Right? So we have to make it half, that is 3 by 2, 3 by 2. So 3, this is the term xy, right? 3 by 2 here. This is the term yx. So here also 3 by 2. So rest all column, the diagonals, right? 6y square. So 6y square. So 7z square, 7z square, right? So this is how, this is very important. In most of the examinations they ask like define a quadratic form, give examples, and represent them in a matrix form like this, right? So this is how we can define quadratic form and how to represent a quadratic form in terms of matrices as x transpose Ax. Okay. So next is the congruence relation. So congruence of matrices, this is also a recap kind of thing. So let us consider two square matrices of order n. Let A and B are two square matrices of order n, such that, so these two are defined, or two are such that B equal to P transpose AP, where P is a non-singular matrix, right? If there is a relation such that B equal to P transpose AP, where P is a non-singular matrix, then what we say is the B matrix is congruent to A. So this is one of the important relation for us throughout this quadratic form concept. This is in terms of matrices, right? So two matrices are said to be congruent if they had this relation B equal to P transpose AP, right? Now, what about congruence relation or congruence of quadratic forms? So suppose we had two quadratic forms. Suppose two quadratic forms, that is, one is y transpose by, other one is x transpose x. Right? So when we can say these two are congruent, when can we say this y transpose by is congruent to the quadratic form x transpose x? Very simple. So when the corresponding, that is, matrices are congruent. So that is when the matrix B is congruent to A. So if the corresponding matrices are congruent, then the quadratic forms are congruent. This is. Now, so now we'll discuss some properties as well as theorems related to quadratic forms. So first is we'll validate the properties which are very familiar, that is reflexive property, symmetric property, transitive property. Right? So I think we remember. So in many contexts we'll discuss these property, reflexive property in general in terms of relations. If you see, if x is in relation with x is in relation with x, right? Then we say that relation satisfies reflexive property. For example, parallel, two lines are said to be parallel. So parallel, if we take as a relation, every line is parallel to itself. Therefore, we say it satisfies symmetric property. It's reflexive property. So what about symmetric property? If x is in relation with y, these two are having relation, implies y is in relation with x. Like a line A is parallel to B implies B is parallel to A. Then we say this relation satisfies symmetric property. So what about transitive property? So x is in relation with y, right? And y is in relation with z. So implies if x is in relation with z, then we say this relation satisfies transitive property. Like A is parallel to B, right? B is parallel to C. That implies the line A is parallel to C. Therefore, the parallel relation satisfies transitive property. Right? So now we prove this in terms of the congruency, particularly congruency of matrices. Right? Once we are working with congruency of matrices, if the same is asked in terms of quadratic forms, right? So the same we have to prove. We'll see it. So first property is reflexive property. That is reflexive property in terms of congruent matrices. So that is we have to prove that every matrix A is congruent to itself. And so very simple here, right? Congruency means we know, right? That is the relation x transpose Ax, y transpose By, right? Now we know every matrix A can be written as I transpose AI, where I is our identity matrix, which is always a non-singular matrix. Suppose if you simplify this, A into I is A, right? I transpose means again it is an identity matrix into A, again what we'll get is A, therefore this holds good, right? That means every matrix A can be written as I transpose into A into I, right? That means it is nothing, that is what we have been telling, right? So then we say this matrix is congruent to this matrix, okay? Where this is the P here, P transpose AP, which is a non-singular matrix, right? So from this what we say is this can be written for any matrix. If you take B, this happens, C, this happens. That means every matrix A is congruent to itself. So that means if it is congruent to itself, that means this congruency satisfies reflexive property. Right? So that means reflexive holds good here. So next is symmetric property. Right? So here what we do is suppose if the matrix B is congruent to the matrix A, right, then we prove A is congruent to B. Why? That is reverse. Right? Okay. So assuming that B is congruent to A, and we prove that A is congruent to B. Right? Suppose the matrix B is congruent to the matrix A. Then immediately we recall the definition, right? So whenever we say congruency, then there exists a non-singular matrix P such that B equal to P transpose AB, right? So whenever this happens, then we say this matrix is congruent to this matrix. Right? So from this we have to say A is congruent to B. So how to prove? Right? So this is from the definition. Right? So now what we do is, so pre-multiply this relation or this expression by P transpose inverse and post multiplication by P inverse. Right? So that's why it is, so B into P pre-multiplication by P transpose inverse post by P inverse. Similarly here, so P transpose inverse is the pre-multiplication and the matrix P transpose AP and post multiplication, right? Okay. And so here we know for any matrix matrix transpose inverse can be written as inverse transpose, right? Like, so here if you see here, P transpose inverse can be written as P inverse transpose, right? Into B into P inverse. Right? So we know this is a matrix, right? This is one matrix and this is its inverse, right? So a matrix into its inverse, it becomes a identity matrix, right? So similarly here, this is a matrix, right? This is its inverse, right? So the product of these two again becomes identity matrix, right? Now if you see this arrangement, so here we had a matrix, some matrix, that is P inverse. Suppose assume that this is a matrix Q, then this is B, and this is nothing but the matrix Q and its transpose, right? That means Q transpose BQ, and this is A, right? Now, so immediately what we say, whenever we find like this, some matrix transpose into that matrix equal to another matrix, then we say this is congruent to this matrix, right? Okay. That is what we have been discussing, right? B equal to P transpose AP, then B is called as congruent to A. Similar way, this A is called as congruent, or A is said to be congruent to the matrix P. Right? Okay. So that means what we have done here is we took B is congruent to A and we prove that A is congruent to, that means the symmetric property holds good with respect to congruence of matrices. Okay. So next, the transitive property, very easy to prove. So that is as discussed while defining. So here assume a matrix A is congruent to another matrix P and B matrix is congruent to another matrix C, then A is congruent to C. The first and last are congruences, right? So very simple to prove, right? So we have to keep in mind whenever see the term congruency, then immediately we have to remember this. Then most of the things becomes very clear. Right? So let us start. So A is congruent to B, then immediately there exists a relation, that is A equal to P transpose PP, right? So A is congruent to B. And also B is congruent to C, right? So immediately there will be a relation, there will be a matrix, right? So such that B equal to Q dash CQ. That means B is congruent to C. So we had these two relations. Now we have to show A is congruent to C. So how to do? We'll say it. So this, from the first one we got this, right? A equal to P transpose PP. P transpose. But from second relation we had this, right? So B is nothing but Q transpose CQ. Right? So now we can write this as, so P transpose Q transpose C into QP. Right? So that is a simple associative property of matrices we used here. Okay. So now we know a simple relation in terms of matrices. AB whole transpose can be written as B transpose A transpose. Right? I repeat, AB whole transpose can be written as B transpose A transpose. Now we use it in reverse. So P dash Q dash can be written as QP dash means transpose, QP whole transpose, right? That is QP transpose equal to P transpose into Q transpose, right? That is AB whole transpose equal to B transpose into A transpose. Okay. So into C, this is not subset, actually C into QP. Now if you see here, suppose if we take this as some matrix R, then this is R transpose, right? So now what is happening? The matrix A is written as, or can be written as R transpose CR, right? So this is our definition, right? So then what we say, the matrix A is congruent to C, right? Okay. So this is how, that means A is congruent to B, B is congruent to C. From that we proved A is congruent to C. That means transitive. So this whatever we discuss is in terms of matrices, right? Suppose if it is asked in the same line, if it is asked us to prove the congruence of quadratic forms, right? How to prove, right? Congruency of quadratic forms is asked. Same way actually. Here only thing is we know, right? Everywhere we have to take the quadratic form. Suppose in this case, right? So suppose if same is asked, prove the quadratic congruency of quadratic forms satisfies symmetric property, then how to prove it? Here we discuss it in terms of matrices. Very simple. So we have to take two quadratic forms. Suppose in this case X transpose AX, right? X transpose AX is one quadratic form, and define another quadratic form, that is Y transpose BY. Right? This is, so first what we have to assume, suppose that this is congruent to this. So assume that Y transpose BY is congruent to X transpose X. Then the corresponding matrices are congruent. So then B is congruent to matrix A. Then we'll prove all these things, right? Just we have to add the quadratic forms before, then we have to discuss in terms of matrices. Here finally A is congruent to B, then corresponding, that is X transpose AX is congruent to Y transpose BY, right? The same we can prove or we can discuss in terms of congruency of quadratic forms. Clear? I think so there won't be any confusion either in terms of matrices or in terms of quadratic forms we can prove, right? So next theorem is the range of values of two congruent quadratic forms, right? The range of values of two congruent quadratic forms are the same. So we have to take two quadratic forms and we have to prove that the range of the value that these two takes are one and the same, right? How to prove it, right? So consider two congruent quadratic forms, X transpose X, Y transpose BY, right? And so here we know, right, whenever two quadratic forms are congruent, then corresponding matrices are congruent, right? That is what we discussed just now also. So immediately we say, suppose you take B is congruent to A, right? So whenever B is congruent to A, then definition, then there exists a non-singular matrix such that B equal to P transpose AB, right? Now, so consider a non-singular transformation X equal to Py, right? So now we had X transpose X, Y transpose By, and this definition B equal to P transpose A. So take a non-singular transformation X equal to Py. So now if we pre-multiply this by P inverse, right? So then what we get, P inverse X equal to P inverse into P, that is I into Y is nothing but that is Y equal to P inverse X. So now what we have to prove? We have to prove the range of values of both quadratic forms are the same, right? So now let us take some value, that is for one particular value will take particular vector. x1 transpose ax1, right? Consider just one value from the first quadratic form, that is x transpose ax. X transpose ax, out of which we are taking x1 transpose ax1. Right? So now, and similarly, we will take y1 transpose by1 from the second quadratic form, right? That means, so we are taking one value from first quadratic form, one value from the second quadratic form, and what we do is we'll try to prove both are the same. Both are the same means the range of values that two quadratic forms takes are one and the same. That is the idea here. So now we took, so y1 transpose by1, and we had this transformation, right, which converts y into x, right? So P inverse x1 whole transpose into P inverse x1. Right? Just now, so we can write this as AB whole transpose can be written as B transpose A transpose, right? So that is x1 transpose into P inverse transpose, B as it is and this as it is. But we know this B is nothing but P transpose AP, right? That we use. So this is what we had. So now we'll take P transpose AP in terms of B. Now what we got is x1 transpose P inverse transpose into P1. This we can take. And A P into P inverse x1. Right? Now if you take this one, we can write this as same like what we have been discussing, and what is shown here is AB whole transpose equal to B transpose into A transpose, right? So now this is a matrix and this is its transpose, right? So we can write this as P into P inverse whole transpose. The reason here is we had P into P inverse, right? And if it is possible for us to have this transpose, then it helps us for us to define the congruence relation, quadratic form, etc. That is the idea here. So now, so x1 transpose equal to this matrix P inverse whole transpose into A into P inverse into x1. But here we don't require this P inverse one, so this is I, right? So this becomes I, this becomes I, then we have to get is x1 transpose equal into A into x1 transpose. That means what we have done here is we took two elements, one element from first quadratic form, one element from the second quadratic form, and finally we are able to prove that both are the same. Right? If both are the same, that means the values that the quadratic forms takes, right, are the same. Right? So this is one property related to quadratic forms. So this is one of the important theorem or property appeared many times in many of the examinations. So it's many times it appeared. If A, B are two matrices such that the roots of det of A minus lambda B, it is not I, because we are habituated to det of A minus lambda I, but here it is with respect to B. Right? Are all distinct, then there exists a matrix P such that the P dash, that is P transpose AP, P transpose BP, both are diagonal matrices. We know what is meant by diagonal matrices, right? So that means all non-diagonal elements are zeros, right? So diagonal elements can be any, right? So all the non-diagonal elements are zeros. So then this is a diagonal matrix, right? So that idea, that clue we use here, right? So if we are able to prove that all non-diagonal elements in this matrix are zeros, I repeat, all non-diagonal, that is the elements other than the diagonal are zeros, then this becomes a diagonal matrix. Here also the same, right? So that is the clue which we use here. Now our idea is we have to prove that the non-diagonal elements of these two matrices are zeros. Okay. So where we have to use this, that is A, B are two symmetric matrices where the roots of this det of a minus lambda v equal to 0 all are distinct. So let us prove. Okay. Okay. So here actually when we see this, we remember the characteristic equation, eigenvalues, eigenvectors, right? Now let us assume lambda 1, lambda 2, so on lambda n are n distinct roots of this equation, that of a minus lambda b equal to 0. Now just to recall this, the previous discussions what we had, when we had this det of a minus lambda equal to 0, so roots of this equation are lambda 1, lambda 2, lambda and so on, they are the eigenvalues. This we are getting like this, then we are saying this matrix is eigenvector, something like this way, right? So that we can use here, right? So let us continue. So let lambda 1, lambda 2 and lambda n be n distinct roots of the equation that of a minus lambda b equal to 0. So then immediately we'll have corresponding column vectors x, right? x1, x2, so on xn. Right? So lambda 1, lambda 2 and corresponding x1, x2 and so on xn, such that ax1 equal to lambda 1 bx1, ax2 equal to lambda 2 bx2, axn equal to lambda n bxn. Okay. So now let them, now we had x1, x2, so on xn, let that matrix is some p equal to the matrix consisting of all these vectors x1, x2, so on xn. So now what we have to show, that is what we discussed, we have, in order to show the matrices p transpose ap and p transpose bp both are diagonal matrices, in order to show this, what we do is we'll show that the non-diagonal elements of both the matrices are zeros. Okay. Now so we'll take two elements, right? Let xi transpose axj and xi transpose bxj are ijth elements of the first quadratic form and second quadratic form respectively. So we took one element from this and we took another element from this, right? And that to here ijth element, because we want to prove that non-diagonal elements means ijth elements, right? If it is I comma I, j comma j, then they are diagonal elements, but our concern is non-diagonal elements, right? So two elements we took. Okay. Now what we do is, so that ax1, ax2, like what we have written right in the first one, this we can generalize. So that can be generalized as axj lambda j bxj. Okay. Now what we are doing is we are multiplying this by xi transpose. Right. So we are multiplying this equation by xi transpose. Then xi transpose axj equal to lambda is a constant or scalar which we can take out, xi transpose bxj. Now so let us interchange I and j. So I becomes j, then what happens, xj transpose axi lambda I xj I bxi. Right? So why we have to do, we'll see it. Why so by doing so what we get, right? So just what we are doing is we are interchanging I and j, we are getting this. Suppose if we take the transpose of this relation, transpose on both sides, right? So xj transpose a xi whole transpose like this, then the same ab whole transpose whatever we have been discussing, right? So now it becomes, so first this transpose xi transpose a transpose and xj transpose of transpose becomes the same, right? This is similarly lambda I, so xi this becomes first, so b transpose xj transpose power and again transpose, it becomes the same matrix. Okay. Now we have been discussing the matrices, whatever we are getting via quadratic forms are always symmetric matrices, right? That means A is a symmetric matrix, B is a symmetric matrix. If A is a symmetric matrix, then A transpose equal to A, B transpose equal to B, right? So now we can write this as, this A transpose can be written as A, B transpose can be written as B. Okay. Now, if you see the two relations we had, suppose if you take the third relation and fourth relation, right? If you see in third and fourth relations, the left hand sides are the same, and right hand side we had something different, right? Lambda j, lambda here, and some relation xi, b, xj, etc. Right? So now what we do is, suppose if we subtract 4 and 3, right? If you subtract 4 and 3, then lambda I minus lambda j into this xi transpose bxj equal to 0. Right? So this is nothing but the roots of the equation, and this is some matrix, right? Combination. Now it is clearly given in the statement itself. All these lambda 1, lambda 2, and so on are distinct. They are different. That means they cannot become zeros, right? This cannot become a 0. So therefore this becomes 0. Right? So whenever this becomes 0, so this also becomes 0 from the equation 3. Sorry. This equation 3, whatever we had, right? So whenever this becomes 0, obviously this also becomes 0. So this becomes. So that means what is happening? Xi transpose AXA, Xi transpose BXA, both are becoming zeros. Now, if you remember the discussion what we had at the beginning, these elements are nothing but non-diagonal elements, right? This is non-diagonal. These are the non-diagonal elements of the first quadratic form. So these are non-diagonal elements of second form. Both are zeros. That means non-diagonal elements of P transpose AP and P transpose BP are zeros. Then obviously what is the conclusion? Then the corresponding P transpose AP and P transpose BP are diagonal matrices. So this is one of the important properties. So whenever the det of A minus lambda B equal to 0 is having distinct roots, lambda 1, lambda 2, so on, lambda n, then for a non-singular matrix P, this P transpose AP and P transpose BP they become diagonal matrices. Okay. So another properties. So this is also many times it appeared in many of the examinations. A necessary and sufficient condition that a quadratic form Q equal to X transpose AX is positive definite is that all the characteristic roots of A are consistently positive. So this already we used or already we discussed in the previous session. Right? So when we tried numericals, when we tried problems related to this concept. Right? So here the quadratic form Q equal to X transpose AX is positive definite if all the characteristic roots of A are consistently positive. So how to prove this? Okay. So here if you see, it is a necessary and sufficient condition. Okay. So that means whenever this is true, we have to prove they are constantly positive, and whenever the eigen values of A are constantly positive, then we have to prove that the quadratic form is positive definite. So how to prove? So the condition is necessary. Right? That is, if we take the Q which is a quadratic form which is of the form X transpose X, and as it is mentioned the eigenvalues, eigenvectors, immediately we recall, so Ax equal to lambda x. So then if we replace here X transpose Ax can be replaced by lambda x, right? So then if lambda is a constant or a scalar, right, we can take out. If we take lambda outside, then what we get? X transpose X. Now if we know X transpose X is what? Suppose if X is a column vector x1, x2 and its transpose is a row vector x1 and x2. If you multiply these two, what we get? Which we have been discussing many times under inner product. Then it will get x1 square plus x2 square, right? So that means this becomes, this we can write this as, if we generalize this, summation I equal to 1 lambda I xi square, right? So this is always positive, right? Always positive. So the total, why total is positive? Because it is positive definite. We know the definition of positive definite, right? Where it is always greater than 0, right? So q is positive definite, that means q is always greater than 0. Q is nothing but this expression lambda I into xi whole square greater than 0. So this is always positive because it is x1 square plus x2 square plus so on, right? So obviously this also, so that is lambda I greater than 0. That means whenever the matrix, whenever this Q is positive definite, then all eigenvalues are consistently positive, that is greater than 0 always. This is necessary. Then sufficient condition. Sufficient condition, what we have to prove? So assuming that the characteristics are distinct and positive, we have to prove that the quadratic form is positive definite. Right? So how to prove? We see. Suppose lambda 1, lambda 2, so on, that is lambda I are distinct eigenvalues. Right? And we know A is always a symmetric matrix. That is the basic definition what we had when we started quadratic forms. So whenever this is A is symmetric, then xi dash, that is x1, x2, so on, are always mutually orthogonal. So then if we take a matrix, that non-singular matrix P is equal to x1, x2, so on, xn, this is an orthogonal matrix. So now we'll take the quadratic form, that is P transpose AP. So P transpose is transpose of this orthogonal matrix to A and this. So this is P transpose and A into the matrix. So then if you multiply, so multiply this x1 A x1 transpose A x1, x1 transpose A x2, like this, if you multiply, so what we get is this matrix, right? So x1 transpose ax1, x1 transpose ax2, and so on. Right? Next, if you go further, x2 transpose ax2, like this we get. So this matrix what we get. And this is nothing but now what happens here is, right? So this becomes our lambda 1. So this all diagonal elements actually, lambda 2. Because this gives a diagonal matrix which consisting of all eigenvalues, if you remember the earlier discussions. Right? So this converts, or this gives a matrix which is a diagonal matrix where the diagonal entries are our lambda 1, lambda 2, so on, lambda, that is eigenvalues. Right? So this matrix. So that is, this is can be written as a diagonal of lambda 1, lambda 2, so on, lambda n. So P dash AP now. So P dash AP is equal to diagonal of lambda 1, lambda, that is a matrix consisting of only diagonal elements which are lambda 1, lambda 2, so on, lambda n. So now we take this Q which we want to prove as definite, right? Q equal to x transpose Ax, right? And take x equal to Py, which is orthogonal transformation. So then Py whole transpose A Py. Then the same AB whole transpose equal to B transpose A transpose, right? So it becomes Y transpose P transpose AP, right? And this is Y transpose into P dash AP, right? That is P transpose AP, that is what we tried just now, right? Previously. So P transpose AP, which is nothing but diagonal consisting of lambda 1, lambda 2, so on, lambda n, right? So Y transpose diagonal of lambda 1, lambda 2, so on, lambda n. Right? So then if we expand this, so here actually Y means Y as a column vector consisting of Y1, Y2, so on, Yn. Its transpose is row vector with Y1, Y2, so on, Yn. And this is a diagonal matrix consisting of lambda 1, lambda 2, so on, lambda n, right? So then if you simplify, then we'll get lambda 1 y1 square, lambda 2 y2 square, and so on. And here it is given in the sufficiency what we have we took. This lambda i's are always consistently positive, right? So this is always positive, and this has to be positive because it is y1 square plus y2 square and so on, always positive, right? So this is always positive, this is always positive, that means q is always positive, right? So that means q equal to x transpose Ax is always greater than 0. So q is always greater than 0 means what we say, this quadratic form is positive definite. This is what we tried. So first part what we have done is taking it as a positive definite. We proved the lambdas are always greater than 0. That is consistently positive. Second part, we took the lambdas are consistently positive and we proved that this quadratic form Q is always positive definite. This is one property or one theorem related. So this definition is also important, and one more property related to this. This is, I think, a new term for most of us. So a matrix A is said to be a gram matrix. Right? Gram matrix. This is a new term, I think we are hearing for the first time. A matrix A is said to be a gram matrix if it can be written as a product of a matrix B and its transpose. Right? So A equal to B transpose B, then the A is called as gram matrix. So this is very useful for short answer kind of questions. So here, so we have one property related. A necessary and sufficient condition that a matrix is a gram matrix is that it is positive definite. So gram matrix means immediately we have to recall A equal to B transpose B. That we have to remove it because this is for the first time we are using this. So necessary and sufficient condition, this matrix A is gram matrix if and only if it is positive definite. Right? This is the property which we will prove. Right? So first one is the condition is necessary, that is what we prove. Necessary means, so by taking the matrix A as a gram matrix, and we have to prove that it is positive definite. Right? Positive definite means immediately the quadratic form Q always greater than 0. If we prove that, then we can say the corresponding matrix is positive definite. Let us prove. So assume A as a gram matrix. So immediately we recall its definition. Right? Okay. So A equal to B transpose B. Then, so we have to prove the quadratic form as positive definite, right? So let us take Q, the quadratic form, which is X transpose X. X transpose X. Now, this X transpose X, now A can be written as, A can be replaced by this gram representation, B transpose B. So X transpose B transpose B into X. Now this can be written as X transpose B transpose is one combination, BX is another combination. So why we have to take is, by taking this we have to prove that this is always greater than 0. Right? So now this X transpose B transpose can be written as BX whole transpose, right? So now it is becoming Bx into its transpose. That means we know it is almost like what we have been using. So Y transpose into Y. Right? We know, right, Y transpose Y is nothing but Y1 square plus Y2 square plus so on Yn square, right, which is always positive, right? Always greater than 0. Okay? So therefore Q is greater than 0. That means Q is positive definite. So when Q is positive definite, then obviously its corresponding matrix is also positive definite. So this is necessary part. So next is sufficiency. Right? So in sufficient, the second part, we have to take the quadratic form which is positive definite, and from that we have to prove that there is a matrix which is gram matrix. Right? So let us take the quadratic form Q, which is X transpose X, which is a positive definite. And let us take the one transformation x equal to py, right? So x transpose x, now use the transformation x equal to py. So py transpose into apy. So here the same like what we have been discussing, AB whole transpose can be written as Y transpose P transpose A Py. Right? So now, so we can take P transpose AP as one combination. Now it becomes Y transpose P transpose AP into Y. Now this is an identity matrix. Right? So this is an identity matrix. So then what we get is Y transpose Y. Okay. So now this Q is Y transpose Y. Now we'll take another transformation. Like what we have been doing is we transformed X in terms of Y by using X equal to Py. Now we'll take another transformation, Y equal to some matrix P into Z. So if we use this here, Y equal to Bz, then what happens? Bz whole transpose, that means Z transpose, B transpose, the same logic, and Y is Bz. Now this can be written as Z transpose into this combination B transpose P, right? So that is Z transpose C into Z, where C is B dash B. Now this Q equal to X transpose X, we transformed into Z transpose CZ, which is always positive definite. So if it is positive definite, then immediately this C is there in the matrix, right? C, which is nothing but B dash B, which is nothing but gram matrix, right? That means whenever Q equal to X transpose X, which is positive definite, then immediately there is just a matrix C, which is a gram matrix. Okay. So gram matrix means it is of the form B transpose B. Okay. So here the important steps we have to remember is this transforming it in terms of Y, transforming it in terms of Z. Right? So that is these are the two things we have to remember when we try to prove this theorem. So next is the Cauchy-Schwartz inequality. So one of the popular inequality when we study inner product spaces. In function analysis, in inner product spaces, this is one of the popular inequality, Cauchy-Schwartz inequality. So what this inequality says is, so consider two real column vectors x and y. Then x transpose y whole square is less than or equal to x transpose x into y transpose y. So they're actually in inner product spaces where they use some other norm, some term called as norm they use. Norm of xy less than or equal to norm x into norm y. That is the term we use when we discuss similar kind of discussion in functional analysis. So here it is nothing but, if you, I think we know, right? So y is a column vector y1, y2 and so on. X is a column vector with x1, x2 so on. Then x transpose y, what we get is x1, y1, x2, y2 and so on, right? So this is. And less than or equal to x transpose x is nothing but x1 square, x2 square, so on, xn square, right? And similarly y transpose y is nothing but y1 square, y2 square, so on, yn square. So why I wrote these two forms is sometimes they can ask without naming, they can ask us to prove this or this. If there exist two column vectors x and y such that prove the first one, or they can ask us to prove the second one also by giving some vectors x1, x equal to x1, x2 so on, xn, y equal to y1, y2 so on, yn, then prove this relation, right? Or sometimes directly they can mention state and prove Cauchy-Schwartz inequality. So it's very simple, just algebraic manipulation we have to do. So yeah, this is what we have to do, right? This is what we have to or we can reverse it. We can, or instead of that, we can take it as x transpose x into y transpose y minus x transpose y whole square greater than or equal to 0. So if we prove this, that means we proved the inequality. Right? So now what we do is we'll take this. So it is actually simple algebraic simplification. So where we have to show that this is always positive. This is when we can say this as always positive. If it is possible for us to write this as product of two inner products, right? If it is possible for us to express this as product of one x transpose y x y transpose y kind of thing, right? So if it is possible for us to write this as inner product of one combination and another combination, right? So for example, it is x transpose x, y transpose y. We know x transpose x is always positive, y transpose always positive. That means product is always positive. That means this whole expression becomes greater than or equal to 0. That is the basic idea. For that, we do some simple algebraic what can call as a manipulation or simplification. So let us start. So x transpose x, y transpose y, and so on. So here we take y transpose y out common. Then it is this we are taking out. So then x transpose x minus x transpose y whole square. This is not there. Therefore, that's why it is by y transpose y. Okay. So now y transpose y into x transpose x. Now we are making this as adding 1, subtracting 1. This term we are making it as minus 2 plus 1. Therefore, minus finally this. Right? Okay. The same term we are making it as minus 2 plus 1. So minus 2 plus 1. So why we are writing this? So we'll try to have some inner product so that both terms becomes positive. Hence, it becomes the total expression becomes positive. Then hence this Quadratic inequality. Okay. So this is what we got. So y transpose y. So x transpose x minus 2 times and 1 time. So now this will separate. So y transpose y, x transpose x. This we separate minus x transpose y into the term. So here x transpose y whole square we separated x transpose y into x transpose y. So that it is x transpose y square by y dash y transpose y minus same actually twice. Now we have separated into minus 1 here, minus 1 here. X transpose y, x transpose y. And this last term we make it as x transpose y whole square into y transpose y whole square. That is multiplying it by y transpose y and dividing by. So this we are making a square. So that's why we are multiplying it by this. That's why I told you this is a simple algebraic gimmick we have to play here. So y dash y. So now we'll take x dash common from this. So x dash if we take common. So x minus, so y into x dash y by y dash y, right? So from these two terms, we took x dash common. So x dash into this minus. From the rest of the terms, we took y dash into x dash y by y dash y. Okay. This is what we have done. So then what we get is this x minus y, x dash y by y dash y, this. Right? So now from this, if you see this, we can factorize, right? So now we can have it as y transpose y, x minus y into x transpose y by this is the common term. If we take out this common term, then what we get is x dash minus y dash into x dash y by this is. So now if you see this is one term, this is another term, this is another term. So here from this here itself we can see if you see the second term and third term. Second term, third. If you take the transpose of the second term, we'll get the third term, right? That is the idea here. So that is we'll proceed further. So y dash y, so second term, third term. So either of these. So now second term as it is, and third term can be written as the transpose of the second term. This is, I think I wrote in the at the beginning. So this is one term transpose. This is the other term. That is almost, it is like y transpose y or x transpose x. We know x transpose x is always a positive term. That is always it is greater than or equal to 0. This is greater than, this first term is also greater than, therefore the total expression is greater than or equal to 0. That means x transpose x into y transpose y minus x transpose y whole square is always greater than or equal to 0. So from this, the Cauchy-Schwartz inequality is proved. So this, I think we need a little bit of practice to do that algebraic simplification in a clever way, so that we'll get the inner product spaces. So last one theorem, if A equal to the matrix Aij is positive definite, then det of A is less than or equal to the product of diagonal elements A11, A22, so on, An. Or this can be written, instead of writing all, we can write this as a product of I equal to 1 to n Aii. So this will prove by taking cases, that is by taking a 2 by 2 matrix, by taking a 3 by 3 matrix, 4 by 4 matrix, and generalize it. So for example here, we'll start with n equal to 2. So here, before going to further, here it is given as positive definite, right? Given as positive definite, and here whatever we are going to prove, it is something related to determinants. Then immediately we have to recall the earlier discussion. Whenever it is positive definite, then it's principal determinants, right? Principal determinants are always positive when it is positive definite. That approach helps us here, right? So positive definite, negative definite kind of thing, where we had some discussion related to its principal determinants, right? That helps here. So now let us take a 2 by 2 matrix. For example, A11, A12, A21, A22. If we take the determinant, so this is A11, A22 minus A12 whole square. Okay, so this is always greater than 0, right? And as discussed, all principal minors are consistently positive. Principal minors means principal diagonal determinants. Principal determinants are constantly positive, and also this term is a square term which is always greater than 0. Therefore, determinant of A less than or equal to the product of diagonal elements A11, A22. So this is for n equal to 2. Now, if I take a 3 by 3 matrix, so quickly we'll go through quickly wind up this discussion with this problem. This case, n equal to 3, this is a matrix. Right? So now we have to go for the determinant of A, right? Determinant of A we can have it in many ways. But here already we had a result where we know something related to this part, right? A11, A12, this one. If you want to make use of this, we have to expand it along a row where this comes into picture. That's why here the expansion is done along this row. That is the reason, so that we can make use of it. So like A33 into A11 minus A12, A21, A22, and rest can be written as A13 into A23 adjoint of the same and A13, A2. So this is, I think, a novel approach. Right? So now the reason here is this, already we are having a clue in terms of this, and whenever the matrix is positive definite, its adjoint is also positive definite. So that helps us here. Okay. So then det of A less than or equal to A33 into this, because based on the previous discussion. Okay. So A33 into this determinant, which is nothing but A11, A22. That means when it is a 3 by 3 matrix, that of A is less than or equal to A11, A22, A33, and so on. So this, if we want, we can take n equal to 4 and do the same way and prove it, or otherwise with n equal to 2, n equal to 3, we can generalize and say that det of a matrix A less than or equal to A11, A22, A33, and so on, Ann. That is about the properties of quadratic form. So this is the end of the topic quadratic form. Okay, thank you.